Testing. 1, 2, 3, 4. Turn yours on.
Testing. I'm John Cleveland.
Okay. Okay, let's get started. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker. But before I introduce today's speaker, I want to recognize some of our students. Each year, our students compete nationally for scholarships and fellowships. And this year, we just received notification that 4 of our students have received nice scholarships from the American Nuclear Society. And each scholarship carries a check for $2,000, and I'd like to recognize these students. First of all, and there's also a certificate here, nice certificate and a letter. The first recipient is Chidima Uwaki. It's not spelled right here.
Thank you.
Congratulations. And the next one is Adam Hetzler. Congratulations.
Thank you.
And then we have Caleb Bastian. Congratulations, young man. And finally, last but not least, is James Bibbins. Congratulations. Okay. Okay, now for the introduction of today's speaker, who is Mr. John Cleveland, who is with the Nuclear Power Division of the International Atomic Energy Agency in Vienna, Austria. John received a BS in physics from Franklin College in Indiana in 1968, and then in 1972 received a master's in physics from Virginia Tech. And from 72 to 74, he worked for B&W in Lynchburg, Virginia. And then he joined the Oak Ridge National Laboratory in 1974, and he was with ORNL for 18 years. After that 18-year stint at Oak Ridge, he joined the International Atomic Energy Agency in 1992, and he's been there for the past 14 years. He's an old friend. I used to work with him when he was at Oak Ridge 2 decades ago, and we've been trying to get him to come and give a presentation for quite some time, and we finally got it arranged. The topic of his presentation today is Overview of Global Development of Advanced Nuclear Power Plants. Ladies and gentlemen, please welcome Mr. John Cleveland.
Thank you, Lee. I appreciate that. Let me say that it's an honor to be here. I watched some of these colloquia on the internet from Vienna. I found them very interesting. I appreciate that UT does that. I even pass them to some colleagues at the IAEA when I know that they would be interested. So thank you very much. It's also a pleasure to be back in Knoxville and see some familiar faces, some colleagues that I've worked with in the past. I'm going to briefly give you a look at the IAEA in Vienna. Then I'll go to my main presentation. And in the end, I want to summarize just very briefly what we do in the Nuclear Power Division at IAEA. The agency was established in 1957 as the Atoms for Peace organization within the United Nations family. Now we have 138 member states, member countries that are members of the IAEA. And we're the World Center for Cooperation on Safe, Secure, and Peaceful Uses of Nuclear Technology. Our Director General is Mohammed El-Bardai. Our buildings are this tall one here and the smaller one next to it. There's also some other United Nations buildings at this center in Vienna. The agency is organized into 6 departments. I list 5 down the side and the one I'm in the middle. We have a Department of Management, a Department of Nuclear Safety and Security, Technical Cooperation, Nuclear Science and Application, Safeguards, one of the main activities of the agency. I'm in the Nuclear Energy Department. We have 2 divisions, the division of the fuel cycle and waste technology. I'm in the division of nuclear power in a section called Nuclear Power Technology Development. Okay, now moving to the main part of my talk. In looking at today's development of advanced reactors, I think it's interesting to start and look at the world's electricity generation since 1950 until now. I kind of chose 1950 because I was a young boy in 1950. But it's interesting that in terms of terawatt hours, those are billion, a terawatt hour is a billion kilowatt hour. In 1950, the world had about 1,000 terawatt hours being generated of electricity per year. Now, just during my lifetime, we have more than 16,000. So it's increased more than 16 times just during my lifetime. And nuclear today produces 16% of the world's electricity, which is more than the whole world had in 1950. Many countries have nuclear power. This chart shows the percentage of electricity that's generated in various countries. France is at the top with 78% of their electricity generated by nuclear power. Japan is down here with 29%, the U.S. With close to 20. All in all, there are 31 countries that get some electricity from nuclear power. And the total terawatt hours last year in 2004, we've collected the data, were 2,619. This shows the numbers of nuclear plants that are operating in various countries. The U.S. has the most with 104. Globally, there are 441 nuclear power plants with a capacity of 367 gigawatts. 26 more are under construction. And significantly, there's been quite a bit of experience. 11,600 reactor years. That's a lot of experience that the industry has. Well, based on information that we get from our member states, we predict that nuclear power will grow. Some countries do have phase-out policies. Germany, for example, has a phase-out policy. But other countries see advantages in nuclear power for energy security, for electricity price stability, and for greenhouse gas reduction. And some countries plan to increase their nuclear capacity. For example, China, India, Japan, Republic of Korea, and Finland. And based on the information on future plans in the various countries that are members of the IAEA, we predict growth from the current value of 2,600 terawatt hours per year to the numbers that I've summarized down here at the bottom of the chart. Now, we're not the only organization that predicts that nuclear power will increase. The Intergovernmental Panel on Climate Change, which is a scientific advisory group to the United Nations Framework Convention on Climate Change, also predicts nuclear power will grow. Now, they've analyzed many scenarios from rapid industrial development in developing countries to slow development. So their ranges for the future nuclear capacity are wide, these yellow bars. We simply plotted the median in this black line, and you can see that's a pretty significant increase out till 2050 from today's installed capacity. But we realize that the future is hard to predict, and so I thought it would be interesting to list what we see as the factors that will influence the future contribution that nuclear power makes to electricity production. One factor, of course, is the degree of global commitment to greenhouse gas reduction. Certainly important are continued vigilance in safety and safeguards. The maturity of the technology is important. It's important to go ahead and implement high-level waste, and public perception and education are important. I want to say a few things about the economics of nuclear power because that's an important area for design organizations that are developing new plants. We did a study recently of what are the means for improving the economics while meeting the very stringent safety requirements that we have today. This was a collaborative assessment that involves several industrial organizations and government agencies, and we got good input from the European Commission and also the OECD Nuclear Energy Agency. we took sort of a quick look at the economics of current plants, and we find that in general they're operating very well. Many of them have already been paid for, they're amortized, so they can generate power simply by buying the fuel and paying for the operation and maintenance costs. They don't have to pay for their capital costs, that's already paid. Many are achieving high availability. The global average availability in 2004 was 83%, and the U.S. did even better at 92%. And these plants are achieving low and competitive electricity production costs. That means fuel costs and operation and maintenance costs. So for example, in the U.S., but also in other countries, lifetime extension and power uprating are pursued because these plants are performing so well. But you also realize that there's fewer nuclear plants being built. I tabulated here, well, during the 1970s, there was an average of 25 construction starts per year. And then back to 1998, you see that the construction starts per year are 3 or 5 or 6 or 1. This year there have been 2 starts up until August of 2005, one in Pakistan and one in Finland. So for new plants, there are economic challenges. The market deregulation that has happened in some countries means that the owners of those plants are no longer guaranteed that they can pay for their plants through a long period of regulated rates. It's a competitive industry now. And nuclear plants have disadvantages with regard to financing compared to fossil plants. It's kind of 3 factors that contribute to that. First, most nuclear plants are large. By large, we mean above 700 megawatts. That's the IAEA definition of large-sized plant. Of course, they cost more per kilowatt electric, so when you combine that large size with the higher capital cost per kilowatt electric, you get a lot of money that needs to be financed when an owner or a potential owner wants to buy a new plant. Secondly, nuclear plants take longer to construct than fossil plants, and they do have higher perceived risk. Either policies, government policies can change, or regulatory delays. So they have these disadvantages with regard to financing. Some more observations. The cost targets for what is going to be competitive for nuclear plants against fossil alternatives, that actually changes due to the market conditions. A good example is United States. Back in the mid-1980s, the Department of Energy started the Advanced Light Water Reactor program. And at that time, we thought that the target to be competitive was about 4.3 cents per kilowatt hour. Now, by the time those plants got developed and certified by the Nuclear Regulatory Commission, the target for being competitive had dropped toward 3 cents per kilowatt hour. So the targets do change with time, and it depends on the conditions in each country. Some countries, it can be more competitive than others because of what they have to pay for fossil and various factors. So it's a country-dependent kind of thing. Some more observations. In this assessment, the experts concluded that electricity production costs, that means fuel cost and operation and maintenance costs, are not likely to fall much below the current best experience of 1.1 or 1.2 cents per kilowatt hour. And so the design organizations have they've clearly focused on reducing the capital cost. And a lot of the design organizations now are saying that their target is about $1,000 per kilowatt electric for the capital cost. Now by that it's an overnight cost, which does not include the interest on their money that they would borrow during the construction period. And it doesn't include their own owner's cost in that process. But the target of about $1,000 per kilowatt would meet about 3 cents per kilowatt hour, which is agreed to be very competitive with fossil alternatives. And the design organizations are working to meet those challenges. They're developing designs, trying to have competitive capital costs, trying to have short construction times. And they've realized that one size doesn't fit all. Some markets, like in France or in Finland, large size plants are what is necessary. But in other markets, and we see this from Vienna, in developing countries, some developing countries are interested in either small size plants or medium sized plants. Our definition of small size is 300 megawatts and below, and medium size is between 300 and 700. So the design organizations are developing plants throughout those ranges. And they realize that to achieve competitive costs, they have to apply proven means, which the industry has already learned can keep the capital costs down, but also they're pursuing new approaches to reduce the cost. And this expert group that I'm referring to has examined that. In fact, back in 2000, the OECD Nuclear Energy Agency produced a very good report that reviewed the proven means for reducing capital cost of new plants. And you've probably seen these kinds of lists before. Certainly the countries that are moving forward with nuclear power are doing it through standardization, designing a plant and building replicates. Japan is doing that, Korea is doing that, India is doing that. That's a proven means for keeping the cost down. Building more than one unit at a site is also a proven means, taking advantage of the workforce and their knowledge and their training. France is a good example of that. They built 58 pressurized water reactors at 19 sites. I've mentioned that keeping the construction schedule short, that means having good techniques for constructing the plant. And I list here some recent plants that have started up since the mid-1990s, and they all achieve very good short construction schedules. One thing that we see in Vienna that's important to developing countries, when a developing country buys a nuclear plant from a vendor in another country, they like to increase and further their self-reliance to build some of the components and systems domestically. That helps them keep their costs down. Also, economy of scale is a key way to achieve competitive capital costs. You see that in countries that are moving forward with nuclear power. In India, they have a series of 220 megawatt electric units, and they recently started up a 540 megawatt electric unit. That gave them economy of scale. They're doing design work on a 700 megawatt electric unit. The European pressurized reactor that is developed by France and Germany takes advantage of the most recent series of pressurized water reactors in those two countries to develop a larger size plant. That's also true in Korea. They've used economy of scale from their standardized 1,000 megawatt electric plants, and now they're planning to build a 1,400 megawatt electric plant. It's true in the United States. The Westinghouse has certified their 600 megawatt electric passive reactor, the AP600, but to get economies of scale, they're working on certifying a 1,000 megawatt electric plant. But we also took a look at what are these new approaches that are being pursued. One that you hear about a lot for small and medium-sized reactors is to modularize the systems, to build them in a factory so that they can have short construction time. Another one is to have highly reliable components, what we call smart components and systems. Improving the technology base to eliminate over-design. For example, better thermal hydraulics codes, better databases, so that we don't have to design in really large safety margins just because we're uncertain about the phenomena or we have uncertain methodologies. And one approach that many organizations are pursuing is to develop passive safety systems for new reactors, where the passive systems are based on natural laws of physics instead of active pumps and components that can operate in case of an emergency. But for those cases where the safety function can be met more cheaply, some design organizations are pursuing passive systems. There's a lot of use of advanced computer-based techniques during the construction phase, even during the equipment procurement phase. One that I think is important, especially in the U.S., is further development of probabilistic safety analysis methods and databases, because this can support simplifying the plant design, and something that the U.S. Nuclear Regulatory Commission has spoken a lot about, which is called risk-informed regulation, which can simplify the requirements on the basis of risk, but it needs good probabilistic safety analysis methods to do that. Coming down to this item, the design organizations tell us that if globally we could establish international consensus on the safety requirements. That would be good for them, because then they could design a plant to be built in one country and build it in several other countries without a big redesign effort to meet safety requirements in those different countries. We're not there yet, but that would be a way to come to more economical plants. And finally, development of systems with higher thermal efficiency. I'm going to give you some examples of that. And expanded applications. I'm going to also give you some examples of that. Okay, let me move now to some examples. Development of advanced designs. That's going forward for every reactor type. Light water reactors, heavy water reactors, gas-cooled reactors, and fast reactors. It's often guided by what we call user requirements documents, where utilities will come together and write what they would require for the next plant. The new designs incorporate the large experience I mentioned from the current plants, over 11,000 reactor years of experience. They also incorporate technology advancements and results of R&D. When we speak about advanced reactors, and our definition is pretty much accepted by organizations around the world, we break that into two categories. We speak about evolutionary designs, which achieve improvements over current plants through some small to moderate changes based on experience. And then we speak about innovative designs, which are more radically different from today's plants, but they may cost more to develop, and they may require a prototype or a demonstration plant before they can be commercialized. I'm going to give you examples of both of these. And when you study the design approaches that the design organizations are taking, you can see that they're meeting very stringent safety requirements. There's a reduction of the operator burden. The operators not needing to react so fastly as they would have in the past. There's incorporation of either highly reliable active safety systems, or in some cases, designers are pursuing this new approach, passive safety systems. They're all pursuing to reduce the core damage frequency. The new designs have a very, very low core damage frequency that's predicted. And they're trying to assure that there's very low releases in the event of a severe accident, so that the emergency planning can take that into account. Well, I wanted to list here several evolutionary light water reactor designs. There's a lot of work going on around the world on these plants. I won't go through each one, but I wanted to show the countries that are doing this work toward evolutionary water-cooled reactors, light water reactors, and the organizations involved, the industries involved. Just to point out, in the United States, the AP 600 megawatt electric passive plant by Westinghouse and the advanced boiling water reactor by General Electric have been certified in the late 1990s by the U.S. Nuclear Regulatory Commission. And now Westinghouse is working to certify by the end of this year to scale up the AP 1000. And General Electric is working to get a design certification for their ESBWR, which is a passively safe plant. But this kind of work is going on in many countries, as you see here. That was for light water reactors. This chart is for heavy water reactors. The development work on heavy water reactors is done mainly in Canada and in India. And Atomic Energy of Canada is working on an advanced CANDU reactor that's light water cooled and heavy water moderated. And India, I believe I mentioned already, has recently started their first evolutionary 540 megawatt plant, which was based on their successful 220 megawatt electric series. And they're doing design work on an evolutionary 700 megawatt electric plant. I want to give some more examples here of the advanced boiling water reactor that's been developed by General Electric and Toshiba and Hitachi. Development of advanced plants takes quite some time. The development of this plant started in the 1970s because the Japanese had a very strict principle of testing new features before they were incorporated into the design. Even if those new features might have been used in another plant somewhere else in the world, they were sure to very carefully test any new feature because they wanted to be sure that their plant operated with high availability once they built it. I list some of the key developments. reactor internal pumps, I'll show you that. Higher improved efficiency turbine. Now the U.S. version of this advanced boiling water reactor was certified in 1997 by the Nuclear Regulatory Commission. Actually, these advanced boiling water reactors are becoming a standardized series in Japan. Right now there are 3 plants operating. The first one started in 1997, Kashiwazaki Kariwa Unit 6. Recently, this year, Hamioka 5 started up, and there's a 4th one that's been connected to the grid and will go into commercial operation soon. So they're becoming a standardized series. And more projects are underway in Japan. There are 8 more projects for advanced boiling water reactors that are in various stages, ranging from planning to environmental impact statement being submitted or the construction permit issued. And there are 2 more under construction in Taiwan, China. Well, I mentioned that they've been improved compared to an earlier boiling water reactor. You see that this recirculation pump, recirculation piping has been eliminated, and the recirculation pumps that takes the condensate water and passes it back through the core have been integrated right into the reactor vessel. So eliminating all that piping was a safety advantage. You all know that in the past years there's been a lot of advances in information technology, and you can see that if you look at the ABWR control room compared to the earlier control room. The information is given to the operators in a much more convenient way. They achieved a 48-month construction period for this plant, which is very, very good compared to some of the plants that were built in the 1970s and early 1980s. They had very good construction techniques. I have a picture here. Their technique that was used at Kashiwazaki Kariwa 6 was called the large block construction technique. They actually fabricated systems at the site or near the site and then lifted them into position with a large crane. So in a way, that's sort of the modularization of the fabrication. And they achieved a 48-month period from pouring first concrete to start of commercial operation. This is all good for the economics of the plant, because then they begin to get the revenue much quicker. And because of the good experience they've had with the ABWR, these are 1,360 megawatt electric units. They've already started work toward their next evolution, an evolutionary, we call it ABWR2, which would be at 1,700 megawatts electric. This is an activity of TEPCO and 5 other Japanese utilities working with reactor design organizations. Their goals are to reduce the capital cost, reduce the construction time, also make them more flexible for use of different fuels, mixed oxide, plutonium, uranium mixed oxide. And they see that these can be introduced commercially in the late 2010s. I mentioned that some design organizations are utilizing passive safety systems. The ABWR 2 is one example where it has a passive core heat removal system and a passive containment cooling system. It doesn't require any emergency diesel generators or emergency pumps to act. It can either cool the core in the case of the core heat removal or cool the containment just by natural circulation. I want to move now to Europe. Framatome has developed the European pressurized water reactor at 1,545 megawatts. It relies primarily on well-proven active systems to achieve a high level of safety. It has 4 independent 100% capacity emergency core cooling trains. It even has provision for cooling a molten core in a very, very unlikely event that the core should melt. I'll show you a picture of that. And it's been approved by the French Safety Authority in October of last year. This is a picture of their severe accident management system. I mean, it's very, very unlikely that the core would melt because of all their emergency cooling trains and their highly reliable systems. But in the event that it would melt and melt through the reactor vessel, they have a spreading area where they can spread the core and maintain it in a coolable geometry. So they've really taken very, very extreme steps to protect against accidents. And we're excited in Europe because now these plants are actually becoming a reality. I show on the left side of this slide the picture of the first European pressurized reactors being built in Finland. I have a picture here of the site excavation. In the background, you see the existing 2 boiling water reactors at that site. And the first concrete was poured in July of this year, so the construction has started. And on the right side, there's an artist's concept of what it will look like when it's complete. I mentioned earlier in my presentation what are the reasons for nuclear power in the future. And TVO, that's the utility that's going to operate this new plant. They already operate the 2 BWRs that are there. They've publicly stated the reasons that supported their decision to buy a new nuclear plant. I thought it's interesting to take a look at that. They said it covers partly the additional electricity demand, and they're going to need to replace some old power plants, some fossil-fired power plants. And importantly, part of their decision was to meet their Kyoto commitments for greenhouse gas reduction, because nuclear plants don't produce any greenhouse gases. So they actually stated that as one of their key reasons. I mentioned earlier that nuclear power can provide stable electricity prices. That was one of their reasons. And they wanted to reduce their dependence on electricity imports, sort of an energy security approach. Moving now to Korea. They're scaling up from their standard pressurized water reactor, which is 1,000 megawatts. They've designed a 1,400 megawatt electric plant. It's been certified by their regulatory agency, and they plan to construct the first 2 units at a site called Shinkori. Moving to the United States, I mentioned already the passive design, the AP600. This was developed by Westinghouse during the Advanced Light Water Reactor Program of the U.S. Department of Energy. Certified by the regulator. Their key developments I list here: passive systems for the various safety functions. They, in the very unlikely event of a core melt accident, they can even retain their molten core inside the reactor pressure vessel. And they have demonstrated these new passive systems by test. So similar to what the Japanese did with their ABWR, they wanted to very thoroughly test the systems before they actually incorporated into a new plant, because that's important. You don't want the new plant to operate at some low availability just because you didn't very well test the system. I mentioned that they realized that they needed to pursue economy of scale to meet competitive cost targets, and therefore they're in the process of getting their 1,000 megawatt electric plant certified by the Nuclear Regulatory Commission. They apply the same passive system technology that they had developed already for the AP600, and they expect to have that certified by the U.S. Nuclear Regulatory Commission by the end of this year. This shows a diagram of one of their passive systems for cooling the containment and condensing the steam inside the containment in the event of an accident, of a loss of cooling accident where the steam is injected in the containment. It's a natural circulation system of air coming in and cooling just through natural circulation the containment wall. And that can be enhanced by a water spray on top of the containment. So it's completely passive, doesn't need emergency diesel generators or emergency pumps to operate. Several design organizations are taking that approach. What I've said now has dealt with what we call evolutionary reactors. Now I want to give you some examples of innovative reactors. And that development is also going on for every reactor type: light water, heavy water, gas-cooled, and fast reactors. A lot of the designs that are innovative are in the small to medium size range, up to 300 or between 300 and 700 megawatts electric. The reason for that is developing countries may want to start with a small to medium sized reactor. They're smaller, they're easier to finance. So that's a factor in some developing countries that want to start a nuclear power program. Nuclear power in the U.S. was started with small reactors. They can have a simple design because they're small. They can employ passive safety systems. And many developing countries see these as something that they could use for what we call non-electric applications. I'm going to give you some examples of applications of nuclear energy beyond making electricity, which I've talked about up until now. But first, let me give you some examples of some innovative water-cooled reactors. One type of innovative water-cooled reactor is a design for conversion of thorium-232 to fissile uranium-233, or for conversion of uranium-238 to plutonium. And I give two examples here. This is to address energy sustainability goals. If you can breed a lot of new fissile material from the fertile thorium-232 or uranium-238, that can help countries meet their sustainability goals. One example is India's work on what they call their advanced heavy water reactor. They intend to fuel that one with thorium oxide so that they can breed uranium-233 as a fuel. They have a lot of thorium deposits in India. This is a vertical pressure tube design. Normally, you know that heavy water reactors have a horizontal pressure tube. These pressure tubes are vertical so that they can achieve the core cooling during normal operation by natural circulation. Other designs for high conversion are being developed in Japan. Those are being developed to convert uranium-238 to plutonium, and they're building on the experience of the ABWR. They changed the core lattice, but they keep the balance of plant similar to what the ABWR has because they've had good experience with the ABWR. Some more examples of innovative plants, what we call integral designs. These are small to medium-sized plants where the reactor core and the steam generator are in the same reactor vessel instead of having the steam generator, in a different vessel. Several countries are developing integral designs, Korea, Argentina, Russia, and Japan. Westinghouse is also developing an integral design, but they claim it's evolutionary instead of innovative because they believe they won't need to have a demonstration plant before they commercialize it, so that's why it's not listed here. But these integral designs are generally small. That means below 300 megawatts. And I'll show you that some of them are designed for both electricity production and seawater desalination. But another innovative design is a water-cooled reactor that operates thermodynamically above the critical point of water. That's above 22 megapascals and 374 degrees Celsius. And this is an approach, you remember on one of the earlier slides I said some approaches are pursuing higher thermal efficiency. Well, this approach promises higher thermal efficiency in the range of 44 to 45% compared to current day light water reactors that have between 33 and 35%. And in fact, this is a design that's been selected for development by the Generation 4 International Forum, a development program, which I'll tell you about in a moment. I want to move now away from water-cooled reactors and talk about the other reactor types, gas-cooled and, in a moment, fast reactors. With regard to gas-cooled reactors, there's a reasonable number of years of experience, 1,565. In fact, most of the nuclear electricity in the United Kingdom is generated by their 26 gas-cooled reactors. These are cooled by carbon dioxide. These carbon dioxide cooled reactors have also operated in some other countries, as I list. More recently, the development work has been on helium-cooled reactors. You remember from your high school physics, helium is an inert gas, and therefore you can operate reactors at higher temperatures and there's no reaction with the core structure as there would be with carbon dioxide. There have been 5 of those reactors that have operated. Those are now shut down, but there are 2 test reactors that are operating, helium-cooled, high-temperature test reactors. They operate up to 950 degrees Celsius. One is a test reactor in Japan. I'm going to show you a picture in a moment. And another one is a test reactor in China. There's also work in South Africa. I'm going to show you a picture. They're developing a small-sized plant with helium coolant. And I list some other countries where development work is also going on. You may have heard about the pebble bed version of these high-temperature gas-cooled reactors. This shows a picture of the fuel. The fuel is contained in billiard ball size graphite pebbles. The fuel itself is in very, very small particles, 15,000 per pebble, and it has coatings on it which will retain the fission products up to high temperatures. So that's one way that these reactors get a very high degree of safety, is through these coated fuel particles that can retain the fission products. A small plant would have very, very many pebbles. And another factor that you often see about these plants, they can be refueled online. The pebbles are put in at the top of the core, and pebbles are then taken out later on at the bottom of the core. This is a picture of the design being developed in South Africa. It's different than a light water reactor that makes steam to go to a turbine. This takes the hot helium at, for example, 850 Celsius, and it goes directly to a helium turbine. And this gives a higher thermal efficiency than the light water reactors. They predict a thermal efficiency of 41 to 43%. And they do promise a very high degree of safety. Number one, because of these coated fuel particles that can withstand high temperatures. Number two, because the core has a lot of heat capacity in it, a lot of graphite that heats up very slowly because of this large heat capacity. They also have a very low core power density on the order of 6 watts per cubic centimeter compared to today's light water reactors, which have about 100 watts per cubic centimeter. Okay, I want to turn now to fast reactors. The history with fast reactors, well, there were test and experimental reactors that were operated in the countries I listed. This led to demonstration and prototype liquid metal cooled reactors that have operated in several countries: France, UK, Kazakhstan, Russia, Japan, and France. The French plant was a large size plant at 1,200 megawatts. It's recently been shut down and it's being decommissioned. The development work continues, and various coolants are investigated. Most of these fast reactors are designed and have operated with sodium coolant, but also lead and lead bismuth, eutectic, and also gas helium is being examined as a coolant for fast reactors. This chart just summarizes the work in various countries. Some of you may remember that the Monju plant in Japan was shut down due to a sodium leak in 1995. The Japanese now are planning to restart that plant in 2008. India is operating a test reactor and constructing a larger prototype plant. Russia is operating a plant. I'll show you a picture of some construction in China. The US and Korea are developing fast reactors also. And we see various roles for fast reactors. The traditional role was to breed fissile material, either by converting U-238 to plutonium or thorium-232, converting it to uranium-233. Fast reactors are also good for incinerating plutonium, and they're good for transmuting the long-lived radioactive waste, both the fission products and the actinides. That can be done either in a fast reactor or in what we call an accelerator-driven system, where the reactor core itself is subcritical, but it receives a particle beam to create neutrons and bring it to the critical state. This is a picture of the 600 megawatt plant in Russia. They recently completed 25 years of successful operation, and that's giving a lot of good experience for future fast reactors. Pictures of the two construction activities in China. The experimental fast breeder reactor planned to start up in 2008, and the prototype larger plant, 500 megawatt electric plant in India. I want to talk about two international efforts that are underway on advanced nuclear energy systems. The first is the Generation 4 International Forum that was started in 2000 and involves, I believe it's 11 countries, mainly industrialized countries, including the US, of course. They're developing new systems. They've stated what their goals are. Their goals come in 4 areas: sustainability, safety, good economics, proliferation resistance, and physical protection. And they've actually developed technology roadmap and selected 6 systems to develop cooperatively, working together, to be ready by 2030. And those systems are a gas-cooled fast reactor, a lead or a lead bismuth cooled fast reactor, liquid metal cooled reactor, a sodium cooled liquid metal cooled reactor, the supercritical water cooled reactor that I mentioned that operates thermodynamically above the critical point, very high temperature reactors cooled by helium up to 1,000 degrees Celsius, and a molten salt reactor. At the IAEA, we have an international project called INPRO. You may have heard of this. That's an acronym for International Project on Innovative Nuclear Reactors and Fuel Cycles. We're looking both at reactors and fuel cycles to support the reactors. This was started in 2000 because our General Conference adopted a resolution that said that we should do this. We now have 22 member states and the European Commission participating. And I think it's interesting to look at what the resolution of the IEA said that the objective, the goals should be. To help ensure that nuclear energy is available to contribute to fulfilling 21st century energy needs. And importantly, to bring together technology holders, those are the industrialized countries, and the users, to consider jointly the actions that need to be taken to assure that we can achieve this. And up till now, they've developed a methodology that the member states can use to assess innovative nuclear systems. That means reactor and fuel cycle. And this methodology is currently being applied by several of the countries to examine innovative systems that could play a part of their future nuclear energy. Okay, in just a few minutes that I have left, I want to talk about the non-electric applications. Up until now, I've discussed making electricity with nuclear power, and I told you that nuclear makes 16% of the world's electricity today. But if you look at the energy consumption, a lot of energy is used in the transportation field, and a lot of energy is used to make heat. And if nuclear can move into those areas, it has a lot of potential to expand. Well, here's some examples of what those areas are. Seawater desalination. The world, a lot of countries are short on fresh potable water. District heating, using nuclear heat to heat residential areas. Heat for other industrial processes. And more recently, there's been a lot of attention on nuclear hydrogen production to provide hydrogen for fuel cell vehicles to displace gasoline in a hydrogen economy. And I just listed some of the ways that nuclear can contribute to making hydrogen. It can do that today because it produces electricity at a low cost, and you can make hydrogen right at the fueling station by electrolysis of water. And then you can also make hydrogen at large central stations through different processes, high temperature electrolysis, thermochemical processes that have water as an input and hydrogen and oxygen as an output. So it's a very clean process. And then there are some processes that are hybrid, electrochemical, thermochemical. There's work going on in all of these areas. It's interesting to take a look at the heat requirements of different applications. Starting at the low temperature end, district heating and seawater desalination, they don't take high temperatures. And moving on up, heat for industry, and at the very top, splitting water to make hydrogen and oxygen. And then you line that up onto the right side with the temperature capabilities of the different reactor types. Now, the water-cooled reactors that I told you about typically make temperatures in the range of 300 degrees Celsius. And this supercritical water-cooled reactor that's being developed by Generation 4 can produce temperatures up to 500 Celsius. And the high-temperature gas reactors up to 1,000 Celsius. So you can kind of match up the applications with the technologies to see how you can make these heat applications. Well, nuclear desalination of seawater is something that's already being done. Japan has several plants that produce electricity but also desalinate seawater. They use that seawater internally for their own use. Kazakhstan has operated a fast reactor, the BN350 liquid metal cooled fast reactor, until 1999, and it produced 80,000 cubic meters per day of desalinated seawater along with some electricity. Pakistan has designed a facility that they plan to connect to their heavy water reactor. India has an operating facility at one of their heavy water reactors, and another one is in commissioning phase. So we are moving forward with desalination of seawater. In Japan, this high temperature reactor, this helium-cooled graphite moderated reactor, could be the first one to demonstrate nuclear production of hydrogen. And a likely process is something called the iodine sulfide process, which is a chemical process that I outline here. But importantly, the input is water and the output is hydrogen and oxygen, so it's a clean process. And just last month, President Bush signed the Energy Policy Act to build a so-called next generation nuclear plant in Idaho. And this plant would be intended to produce hydrogen and also electricity. And that's an artist's picture of what that plant would look like. That really completes my overview of global development. I wanted to just say a few things about what we do at the agency. I haven't said that yet. One thing we're able to do, we see what's going on through contact with our member states. We see what's going on in reactor development around the world. And I think that's one thing that's very exciting to me in working at the agency, to understand and see what's going on around the world. I wanted to sort of show you our statute, why we do these things. Our statute says that we should encourage and assist research and development and practical application of atomic energy for peaceful uses, and that we should foster the exchange of information, scientific and technical information, and we should encourage training of scientists. So our activities in the division that I'm in, which is the Nuclear Power Division, all come from this part of our statute. And we feel like we're working toward nuclear power's renaissance. We believe there will be a renaissance in nuclear power. We had a large conference in Paris earlier this year. It was a ministerial level conference where we asked governments to come and tell us what their plans are for the future. What do they see? And many governments came and said they see nuclear as part of their future. Not only the countries that are operating plants today, but also other countries that plan to implement a nuclear power program. And our objective is to foster the efficient and safe use of nuclear power, and I just listed some of the actions that we do. One of our actions is to maintain what we consider balanced and objective information. We try to publish every 4 or 5 years status reports on each reactor technology, and these are technical documents. We don't allow any advertising from one vendor to compete with another vendor. We present these status reports in a balanced and objective way. We also try to foster collaboration on advanced plant development. We try to catalyze innovation toward new and advanced plants. For the operating plants, we have activities to improve the training of the operators and their performance, and we have activities to assure that they have very, very good management approaches. And we try to assist new countries that are planning to establish nuclear power with establishing their infrastructure that they would need to implement a nuclear power program. So within our nuclear power division, we do all of these activities. And I would invite you to get onto our website and see a lot more details. I've kind of grouped these bullets. The top 6 mainly focus on good operation of current plants, quality assurance, quality management, training, life management, which is important. A lot of plants are extending their lifetime, and a lot of plants are improving their instrumentation and control system. And the next set of bullets is what we do for advanced reactors, some of the things I've mentioned. We have activities on high temperature gas-cooled reactors. We have activities on advanced water-cooled reactors, fast reactors, desalination of seawater. And finally, the bottom one there is you can read about more information on our international project that's looking to see how we can meet the world's needs for the 21st century. So I very much am glad that I could be here, and thank you for your attention. I'd be happy to answer some questions, try to answer questions.
Dr. Dodds had to leave. He is on his way to France to attend a conference. We have time for a few questions for Mr. Cleveland.
Yes, Mario.
John, in this country, a lot of the people who work in this country, the people who work in the nuclear industry are getting old, and they're retiring, and we have to develop young people to take their place. Now, you see the nuclear work that's being done throughout in other countries throughout the world. Do they have the same problem where the nuclear people are old, or do they have a more balanced level of ages?
Well, unfortunately, that happens to all of us. Yeah, let me see what I can say just from personal observation. The Korean nuclear program has been very well respected inside the Republic of Korea, and I see a lot of young Korean engineers when I go there. So, but I think that's because their program has been dynamic and moving forward and building new plants. I think maybe we got a little bit old because there was kind of a lull in U.S. nuclear energy, but I was glad to hear from Professor Dodds today that, and I heard it last week at Oregon State University, that enrollment is really up. And I think young people are realizing they've got a real concern for the environment. They've seen some of the predictions for the global warming, and nuclear has a very, very good safety record. We had 2 accidents in the past, but we don't do things that way anymore. And I think the youth are realizing that nuclear is a very safe and a very clean technology, and I think they're coming back. So maybe that's a partial answer to your question.
Any other questions for Mr. Cleveland?
John, I noticed that in terms of startups of new reactors, China had not started a reactor building a reactor since the year 2000. That kind of surprises me given the demand for electricity in the country. Can you explain why that's happened?
They definitely have plans to expand their industry. I didn't realize they haven't had a construction start since 2000. We do have a publication in Vienna that documents the construction starts, but also documents the plans for new plants. And I'm sure that if we could study that, we'd see that China does plan to build quite a few new plants. I can't quote the number of megawatts in the next few years, but they do have an active program. They've solicited bids recently for new pressurized water reactors. So I think if it wasn't on my chart, you'll see it on there very soon.
Any other questions? I have a question for you, John.
Yes, sir.
Would you comment on the internship program for students at IAEA?
That's a good point. We do cooperate with the World Nuclear University, and you know they had their first summer session this year at Idaho National Laboratory. We also have other education activities. I know that in my area, which is technology development, we have some courses that we feel are useful that really came sort of a spin-off from international collaboration on technology development. So I guess I can't say, I can't give you an overview of what the agency does, but I can say that we're very interested in knowledge preservation and in training and education.
Okay, very good. Any more questions? Okay, before we adjourn downstairs for refreshments, everyone is welcome. I see some new faces here. Let's thank Mr. Cleveland again. Thank you very much.
Thank you.